Welcome back to our course on microwave filters. So in previous classes we have seen how a low pass filter can be transformed to a band pass filter or band stop filter or even a high pass filter. So we have seen various kind of transformations so that we can transform a low pass filter to an equivalent high pass filter or a band pass filter. We have seen in previous class how we can, for example, if we want to transform to a band pass filter, so how an inductor can be replaced with a series combination of inductor and capacitor, and a parallel capacitor can be replaced with a parallel combination of capacitor and inductor. So in this class, we're gonna do a design example for a band pass filter. So as we have seen, like if we know certain things about the filters, the filter characteristics, so the first step is to design a low pass filter, and then we have to scale up and we need to transform to the right frequency, right impedance, and the right transformation, say band pass filter in this case. So let's start with a design example on band pass filter. So we are considering a problem here. So I'm not writing the whole text. So we need to design a band pass filter with 0.5 dB of ripples, and the order of the filter is given as 3. The center frequency is 1 gigahertz, so it is assumed the center frequency is equals to 1 gigahertz, and it is given the bandwidth is 1% around this center frequency, and the system impedance, the Z0, is given as 50 ohm. So as I have already explained to you, so just we need to design a low pass filter first. So as this is having certain ripples in the pass band, so it most probably it would be a kind of Chebyshev design. So it is quite obvious, like it is a Chebyshev design. And in previous one of the design examples, we have shown, like for a particular ripple factors in a pass band, how we can get the G parameters, or those G parameters can also be directly taken from the tables provided in POSARs for different ripple factor like 0.5 dB or 3 dB. So in order to start with this problem, we are taking those G parameters from the table. So let's start with taking a G parameters from the table. So we have seen if the order of the filter is odd for Chebyshev filter, so we have Gn plus 1 is equals to 1, and G0 is given here as 50 ohm impedance, so we have taken as a normalized 1. Now other GKs, so we have order of the filter, so this is G4. So what we left with, it's 1.5963, and G2 equals to 1.0967, and we know that with these topologies they have some symmetry, so G1 is equals to G3. So now we have the G parameters. We have taken these G parameters directly from the table. So we didn't get calculated here, but we know that the equations for calculating the G parameters, and we have used those in the previous class. So for this problem we are just taking as these G parameter from the table. So the next thing is, so suppose we have G parameters, so the low pass prototype for this 3 third order filter is somewhat like this. So this is G1, this is G2, this is G3. So here we have a series inductor, here we have a series inductor, and here we have a parallel capacitor. Okay, so here is our. So there are two ways. So we need to perform the frequency scaling and impedance scaling. We can do that scaling at the low pass prototype as well, or we can do that at later stage as well. So in previous class we have seen this series inductor can be replaced by a combination of series inductor, say this is L1, this is C2, and this is L3. Then this would be L1 dash, C1 dash, and this could also be replaced with a series combination of an inductance L3 dash, say suppose C3 dash, and this can be replaced by a parallel combination of a capacitor that could be C2 dash and L2 dash. Okay, so if we want to translate this low pass filter to an equivalent band pass filter, so we need to replace this series inductor to a combination of inductor and capacitor, and so on and so forth. So how these quantities are related we have seen in previous class, how we can transform these inductance and capacitance into the equivalent inductance and inductor and capacitor value at say band pass filter. So these equations can be referred directly from so let's say what would be the value of L1 dash. So L1 dash would be the L1 into Z naught divided by omega naught into delta. So I'll explain what is delta here is. So this is for this series combination. Similarly, if we talk about C1 dash, so C1 dash is equals to a delta divided by omega naught L Z naught. So this transformation is for a series inductor to a series combination of inductor and capacitor. So that the same configuration can be used for this inductor. So if we write this combination for this combination for this series combination of inductor and capacitor, so let's say L3 dash gonna be L3 Z naught divided by omega naught into delta. And similarly for this combination, the capacitor value would be delta divided by omega naught, and this was L1, this is gonna be L3 and Z naught. So we have seen these transformation, how we can get these values in previous class. So now it's time to write the equivalent value for this capacitor and this inductor for a parallel combination. So for this, the C2 dash can be written in terms of C2 in the following form. It would be C2 divided by omega naught delta Z naught, and the L2 dash divided equals to is delta Z naught divided by omega naught C2. So this is a kind of a transformation that we need to perform in order to translate this low pass filter to a band pass filter. So by solving these all the equations, we can get these values L1 dash, C1 dash, and we can make an equivalent band pass filter. So how this is gonna be translated? So let's see. This L1 dash gonna be replaced with a series combination of inductor and capacitor, and this parallel capacitor going to be replaced with the parallel combination of capacitor and inductor, and similarly here we have another series combination. So this value gonna be L1 dash, C1 dash, this, and this gonna be L3 dash, C3 dash, and this C2 dash and L2 dash. So this is the transformation, and this would be your band pass filter. Okay, then here we have a source and some load impedances. So suppose this is your 50 ohm, this is your 50 ohm. So let's calculate these values based on the given like parameters. So let's define, there are few things that those are not defined here. So let's define those values. So first thing is given as omega naught is equals to 1 gigahertz. Okay, and there is one term delta which is defined as F2 minus F1 divided by Fr or F naught, or in terms of omega, if we write omega 2 minus omega 1 divided by omega naught. So if the problem is saying the bandwidth is basically the difference of two cutoff frequencies, the high pass and low pass, which is equals to the 1%. So if we write this delta with the help of, we can write directly delta is equals to 0.1. Okay, then what else left to calculate the value of L1? I think we have all the values. So L1 dash which is equals to L1 Z naught divided by omega naught into delta. So L1 we have calculated, this is equals to G1, and G1 here is 1.5963 into Z naught. We have a system impedance as 50 ohm, omega naught 2 into pi and 1 gigahertz 10 to the power 9, and delta equals to 0.1. So this is going to be value of L1 dash. So let's have a C1 dash. So C1 dash is delta divided by omega naught L1 Z naught. So if we place all these values, 2 into pi into 10 to the power 9 multiplied by L1 is 1.5963 multiplied by 50. So we can solve C1 and we can get these values by solving these expression. In similar manner, if we want to calculate say C2 dash, C2 dash, which is equals to C2 divided by omega naught delta Z naught. C2 is equals to G2 and G2 is given as 1.0967 divided by 2 into pi into 10 to the power 9 into delta into system impedance 50. Similarly, we have L2 dash so L2 dash is equals to delta Z naught divided by omega naught C2. So if we place all the values, omega naught going to be 2 pi to 10 to the power 9 and C2 is equals to 1.0967. Now the another combination, as we know that this G1 equals to G3, and so we can say that this L3 gonna be same as the L1 dash. So the next calculation, like L3 dash gonna be equivalent to L1 dash, and C3 dash is gonna be equivalent to C3, only C3. Okay, so we need to do these calculations. So we can use calculators to solve these equations. Say for example, the first value of L1, so let's calculate it. 1.5963 multiplied by 50 divided by 2 divided by pi divided by 0.1. So this comes out to be 0.127.09 into 10 to the power minus 9, and which can be written as 127 nanohenry. For solving this, so if we solve this, so 0.1 divided by 2 divided by pi divided by 1.5963 50, so it comes out to be 0.199 picofarad. So I have pre-calculated these values, so I'm just writing those pre-calculated values. So L2 dash is equal to 0.725 nanohenry, and L2 dash, sorry, this is C2. So C2 dash is equals to 34.9 picofarad, and L2 is equals to 0.725 nanohenry. And these values we can, like L3 dash is equals to L1 dash, and C3 dash equals to C1 dash. So let's put these values on the filter. So L1 dash is equals to 127 nanohenry, and this capacitance is 0.199 picofarad. Similarly, here also we have this as 127 nanohenry, and this capacitor value is 199 picofarad. This is equals to 0.725 nanohenry, and this capacitance is 34.9 picofarad. So this completes the design of a bandpass filter with having a cutoff frequency is in the lower, say the for pass like low pass filter, but here we have this as a center frequency of the bandpass filter. So this completes the design procedure. The next step is to take these values to any simulator and try to plot what's the frequency response of this filter.